if you have two matrices, we know that they don't always commute. A lot of times you could if you compute AB and BA, in many cases they are different. However, sometimes they do commute. They do commute. Sometimes that happens. And one of an example like that, and actually this is a very deep subject. Like the question is like, when does AB equals to BA? That's the question, right? And there's an answer that you wouldn't understand at this point. The answer is like, if A, B have same eigenvectors, or another way to say it is that they're simultaneously diagonalizable. But we didn't even go through eigenvectors yet. Yeah. But just to give you some examples of such, think of A squared and A. Now these two clearly commute, don't they? Right? Because if you have A squared times A, that's A times A times A, which is A cubed. And if you have A times A squared, that's also same as A times A times A, which is A cubed. So they're equal. So A squared and A commute. And then you also have A to any power commuting with A itself. So A to any power and A to any other power, they commute, right? What that means is that if you limit yourself to just matrices, just the exponent of a single matrix, then you don't have to worry about commutativity. Now, if you wrote down all the properties of matrix multiplication, they satisfy almost everything that you know of that regular real numbers satisfy, right? Associativity is true. That's why you're doing this. There's also multiplicative identity. The identity matrix it works like that, right? And so many other things are true. There's also this distributive property that's also true. But then there's one thing, actually there are two things that don't work like the real numbers do, and one of them is commutativity, right? Real numbers, when you multiply two real numbers, they commute. Whether you do 3 times 2 or 2 times 3, they're the same thing. And the other one is, for real numbers, all numbers except 0 are invertible, right? You can take the reciprocal. You get a multiplicative inverse. Whereas for matrices, they're more than just 0. There are other matrices that are non-zero but still not invertible. That's because if the determinant is 0, you don't have an inverse. Right? But then you can kind of see that if you limit yourselves to only matrices that commute amongst themselves, and then if you also allow them to be invertible, then the things that you calculate them, you can calculate as if you're doing calculation with real numbers. Right? And such an idea is what gives rise to this polynomial of matrices. So suppose you have a matrix Px equal to x squared minus 2x plus 3. Then if you have a polynomial, you're supposed to only plug in real numbers, but you can take that polynomial and plug in a matrix. Just like that. Matrix. And then we need to write down what that means. That means I'm replacing x by a, but then because in the multiplication of matrices, what acts like 1?
The identity.
The identity matrix, right? So you can think of 3 as 3 times 1 and replace 3 times 1 as 3i, where I is the identity matrix. And that's called the polynomial of matrices. And because now, if you only limit yourselves to powers of a, then you can have things like if p of x times q of x is r of x, if pq are 3 polynomials, then it will still be true that p of a times q of a is equal to r of a. So if you have any x and make a polynomial, let's say you have a polynomial of degree 3 or less, mathematicians call such an object as a ring. Maybe if I go there, it's going to be too much. Yeah, so it just has all these properties. You can do everything that you were able to do on here to do it here. Okay. All right. So let's try to see how it helps us. Okay? So let me give you an example problem. So here's a question. Let's say A is given like this. A is compute P of A if P of x is x squared plus x plus 1. Okay. B, using x minus 1 times x squared plus 1, x squared plus x plus 1 equals to x cubed minus 1. Do you know this identity? You learned this in high school algebra?
I should.
Yeah. Okay. I mean, if you tutor in the Learning Center, you may see this, right? You see it, right? Okay. Yeah, that's why you want to teach other people basic math. If you don't, you forget these basic ones. Okay? Oh, using this, compute a to the third. And C, now compute a to the 101 power. Let's to figure out what a to the 101 power is. Now, imagine multiplying -2, -3, 1, 1 by itself many, many times. That's going to be a lot of work, right? So you probably don't want to do it. But with the help of matrix polynomial, we'll be able to get this answer. We'll be able to find some pattern. Actually, for this question, you can just start from a squared, and a cubed. At some point, you'll find a pattern. But that's no fun. So I'm just trying to suggest a slightly different method. All right. So let's try this one. Part A is asking us to do P of A, which is a squared plus a plus 1. No, identity, because any constant has to be promoted to that constant times identity. That's how you make a matrix polynomial, right? Okay, so for this one, let's do -2 times -2 is +4. -3 times 1 is -3. So 4 minus 3 will be 1. -2 times -3 is +6. -3 times 1 is just -3, so it will be +3. 1 times -2, 1 times 1 will be -1. 1 times -3, 1 times 1 will be -2. So that's what I get. You know how to multiply matrices, right? Across, down. So that's all I did. And that allows me to write a squared as 1, 3, negative 1, and negative 2. And matrix A should be the original one, negative 2, negative 3, 1, 1. What's the identity matrix? 1, 0, 0, 1. So we had 1 plus negative 2 plus 1. What's that? 0. 3 plus negative 3 plus 0. 0 again. Negative 1 plus 1 plus 0. Oh, 0 again. Negative 2 plus 1 plus 1 is? 0. Huh. That's nice. Okay. Now, part B says, using this identity, this is something that you may or may not have seen in high school, but it's very easy to check that this is true. Just FOIL out and you'll see mass murder. You want to see mass murder? X times x squared is x cubed. X times x is x squared. X times 1 is x. Minus x squared. Minus x. Minus 1. Kill. Kill. Oh, I may have to edit this out. I might get in trouble. All right. So anyways, that's what it is, right? Okay. So I have this, and then my point of introducing this polynomial, matrix polynomial, is the sole fact that anything that you do with polynomials, you can do again with matrices, because if you just limit yourselves with A, then all these things commute, and every calculation you can do with X now can be done with P of A. Now, you should realize that sometimes you have polynomials in two variables, right? Something like x plus y times x minus y, something like this. And I know that this is equal to x squared minus y squared. Right? Now, for polynomials with two variables, you can't do such a thing. If you plug in a and b in here, you'll see that this is not necessarily the same as that one because of lack of commutativity. So once you get to two or more variable polynomials, then you can't. It's not fun using the matrices. I mean, you can still do it. Sometimes people do use it. But at least for one variable polynomial, everything works exactly like this. So if I have that, I have the same exact identity in terms of matrix polynomials, which is a minus identity times a squared plus a plus identity is equal to a cubed minus identity. This is the polynomial version of this. Again, if you want to check that, if you're suspicious, you can also expand this out exactly like what we did over there. A times a squared is a cubed, a times a is a squared. And you'll see lots of cancellations, and you get a cubed minus identity. Yeah. So it is really true. And note that this has nothing to do with this result. It's just that this is always true. Yeah. For any matrix A, this is always true. However, because of this first result, we know one more thing. What is this? We just did it. What is it? The zero matrix, right? It's zero. It's not zero as a number. It's a zero as a zero matrix. Okay? If this was a textbook, you would write this as a bold font. Okay? Just like you use bold font for vectors and regular font for variables, reals. You would do that. Equals to a cubed minus identity. And any matrix times zero matrix is? Zero. And therefore a cubed is? Identity. A cubed is identity. Okay, so that's the answer to part B. Now let's move on to part C. How would you do a to the 101 then? This is a to the 99th power times a squared, where a to the 99th is the same as a cubed to the 33rd power, a squared. What's a cubed again? What's identity to the 33rd power? Identity. So you get identity times a squared. Therefore, you get just a squared, which is that matrix that we just did. 1, 3, negative 1, negative 2. Done. Okay?
So I have a question.
Yes.
With the first matrix that you had, why did you change it to that?
Okay, so yeah, I'm going to cut the previous mistake. In the previous part, I had the signs wrong and it didn't work out, so I had to fix it.
So it only works with a certain matrix?
Yes, yes. So these are really good questions. So there should be lots and lots of questions that appear right from here. Okay? This single question should give rise to many other questions. One question is, how did I know that this is going to be 0? That's one question. Question number 1. Okay? I'm going to address that. Right? Number 2, what if this is not 0? What do you do? Well, there are some other methods that you will learn later. Okay? Not today. I might mention a little bit. Okay? Number 3, third question is, why would we want to know a to the 101 power? What good is it? Okay?
Shortcuts.
No, there are some other reasons. Okay, so those are some questions that you should have.
Is there a reason why you want to know to the 101 power? Because to prove the identity?
So I was able to ask the 101 power because I knew that this is going to be true. I knew that this is going to be true because I knew this identity and I knew that this is going to be 0. Okay? So in my mind, when I first wrote down the question, I started with the matrix that this would work. Okay. So of the 3 questions, let me just answer the first, the last 2, because those are, I can't give a full answer, but it gives you good motivation, and then I'll try to address why I knew that this should satisfy this equal to 0. So to give you the answer to, actually let me do it in reverse order. Okay. So in reverse order, so the last question, question 3 was, why would I want to know a to any power? Is that any good? Okay. So what good is this? Well, there are many applications that rely on knowing this. One such an idea is if you had an equation like x prime y prime equals to -2, -3, 1, 1, xy. Ooh, what's that? That's system of differential equations, right? Yeah. Some of you remember, some of you may not have taken differential equations, so you might not know. But see, this looks like, if I call this as big X, it looks like x prime equals to a times x. Isn't that right? And if you have, let's say x and y are both functions of t. So big X is a function of t, okay? Then you can check that if you set xt as some initial value x0, y0, some column vector like that, times e to the at, right, then this will satisfy that equation. So forget for a moment that A is a matrix. This is ridiculous, right? Not only we are plugging in a matrix into a polynomial, we're plugging in a matrix into a function. That's like, what does that mean? It's really strange. But if for a moment you just let that go, then you know very well what the derivative of this is. What do you get if you differentiate this?
A.
A comes down, right, because of the chain rule, right?
Yeah.
And that exactly gives you that left side. If you see, if this is true, then x prime really is A times xy0 ECAT, and we decide to call this one as your x, right? So it satisfies the original equation. Isn't that right? Yeah? Okay. So you immediately see that, oh, if you know how to take the exponents of matrices, then you can solve systems of equations, systems of differential equations. In my class, my differential equations class, we didn't have enough time to cover all this, but in some other schools, the differential equations in SUNY Maritime, we cover a little bit of PDEs too, because we don't have a separate PDE course in the engineering program.
What are PDs?
Partial differential equations.
Oh.
Yeah.
That's a whole separate class?
It's a whole separate class, but we do teach a little bit at the end of the differential equations. But in many schools, they have it as a separate class, and they devote a whole entire, like 2 or 3 weeks into doing more of this. So if you are in that class, you would know, right? So you're kind of getting the things that you missed, right? So now the question is, you just need to know how to exponentiate the matrix, right? How would we do this? Because if you know this, then this is not very different, right? It's just multiply by a scalar and you do it. Yeah. So how do we do this? Any ideas? How do you take exponentiation of a matrix?
Would you like expand the matrix and do it like one by one for each value?
1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. Right?
I love that.
What's that? That's an infinite polynomial, and we know how to handle polynomials, right? So what would this be then? E to the A would be what? Say it. What? Huh?
1 plus.
Huh?
1 plus.
No, it's not 1. There's no 1 here.
I.
Thank you. Yeah. The identity matrix.
You said what you said?
Yeah. Okay. 1 over 1 factorial A. 1 over 2 factorial A squared. 1 over 3 factorial A cubed.
I'm gonna rewatch.
So, okay. All right. Okay, maybe this is not suitable for recording, but who cares? Nobody watches my videos.
Nah, we
All
don't.
right.
You have like
Okay, no,
20,000.
all right.
Summer course.
Okay, so going back, so we have then, that's the matrix exponent. And in here, what do you see? You see a to the nth power. Right? So if you can figure out what the nth power is in general, that enables you to write down things like that. Okay? So that's like one thing, and there are some other applications of this. So in graph theory, if you want to know the probability from one going to some other place, let's say you have all these bunch of nodes and there's the connections, and if you have a random point here, the probability of going here is 1/2, that's like 1/3, and there's 1/6, and then you have all these probabilities. And if you want to know what the probability of this one ending up there, that's called a Markov chain. We might have time to do that. Then this transportation matrix can be taken to nth power to find all kinds of probabilities. So that's another case that you would use that. Okay. So I answered the third question. That's a good answer, right? You agree that that's a good answer, right? Okay. Now let's try to answer the second question. Why would we? How would we find the nth power in general? Well, so second question is, how do we find a to the n in general? Because for this example, if we were lucky, it somehow a squared plus a plus identity was 0, and that enables us to find the solution in general. And the observation, there are two observations. To answer this, there are two observations. Number one, observation one, is that if you have a diagonal matrix, then it's really easy to calculate the nth power. What's that? It's just simply a to the n, 0, 0, b to the n. You can just do it. It's like a, 0, 0, b, a, 0, 0, b. What's that? A squared, right? This will be 0, this will be 0 again, and this times this will give you b squared. Right? Then you multiply it again. So this is true for diagonal matrix. And then observation 2 is that if you have no, that's not true. If you have so P inverse A of P, that's called a conjugate matrix of A. Okay, so take any matrix A, and then you conjugate with some invertible matrix P. So this is called a conjugate. If you take the nth power of this, that's like repeating this many, many times, right? P inverse AP. So repeating this many, many times, so the total number you write is n, right? But then when you do that, these things cancel each other, right? This will cancel, and then eventually these things will cancel, and all the a's will survive. So therefore, at the end of the day, you still have P inverse in the very beginning and P at the very end. But the middle one, all the p's cancel, and you just have a to the nth power. Okay? And therefore, out of these two observations, what we wish for is, so here's our wish. Okay? Here's our wish. If if we can find, this is a better word, if we can find P such that, so let's say somebody gave us the matrix A, okay? And if you can find a P such that P inverse of A times P is a diagonal matrix, D for diagonal, okay? Then we can just take nth power both sides. Nth power on the left side is this. That's what we just figured out, right? And nth power of a diagonal matrix is easy, as we know, right? So therefore, you can just say, you can multiply P both sides here, so it's P d to the n, and then P inverse to the other side. It's like that, okay? Oh, one thing that you have to be careful is that when you multiply matrices, you have to be aware of which side you're multiplying. So to cancel P inverse, you have to multiply P on the left side, right? So your P has to be on the left side. To cancel this P, you have to multiply P inverse on the right side, so it has to be multiplied on the right side. Unfortunately, matrices don't commute, therefore you can't move this across the d to the n to cancel the other one. It simply doesn't work that way, okay? But as you can see, this is easy to calculate, and these will be doable, so that you will get a general formula. Okay? And that's like a generic plan. So a lot of the linear algebra will be devoted to this question: when can we find some kind of a matrix that would make the matrix look diagonal when you conjugate it? Okay. And the answer is, sadly, you can't for all cases, but in most cases you can. That's the so for most of the matrices, if you randomly generate a matrix using a computer, 99.9% of the time it will be something that can be diagonalized. assuming that you're generating your numbers as like decimals. If it's integers, it might, like with some limits, it might have some more probability of not being diagonalizable, but there are a few matrices that can't be diagonalized, and therefore you can't use this idea. And we will not only learn how to do it, but we'll also learn why sometimes our strategy will fail. Yes?
So is that matrix that you showed us in the beginning, that was not diagonalized?
This is not a diagonal matrix, but it can be diagonalized, I think. It's, let me see. Minus lambda. Oh, okay. So it can be diagonalized, but you need P to be some complex matrices. What I'm doing is I'm doing the eigenvalue equation. Yeah, yeah.
Diffuse.
Right, right. Okay.